Hi guys, thanks for joining. Not going to introduce myself for the third time. So, hi, I'm Jorik, and that's all I'm going to say about that. So, the goal of this session is that, as you have heard, this summer school is organized by EUDAT together with DICE. And DICE is a European project. And part of this project was that we were going to help communities. And in this session, I will present one of the community use cases, publishing the LOTS data sets. And later, so at 10, so not everyone will be able to join, unfortunately, a colleague of mine, Nargis, will join another collaboration between DICE and a community, and that will be for Combiomed. So, somewhere in a country far, far away. First question, who knows where it is? And second question is there anybody in the room that knows what they're looking at? First location. And when I say somewhere in the country, not far, far away, I actually should say in a country not that far away. What was your guess? Netherlands, yes, correct. This is in the northern part of the Netherlands. And do you know what this is? I don't think so. I've seen some puzzled faces.
It's quite like solar panels.
Solar panels? Not completely, although there are solar panels in that field. No, this is a part of the LOFAR, and the LOFAR is the low frequency array, and this is actually a very, very big telescope. So this is the main field of the LOFAR. This is all the squares you see are basically antennas, and they're not only located in the Netherlands. Or not only located in that location in the Netherlands. There's 38 stations in the Netherlands, and then there's 15 stations in other countries. And LOFAR has been around for a little more than 10 years. So the International LOFAR Telescope turned 10 in 2020, and the whole project starts a little bit earlier. And LOFAR is a radio telescope that can be used by researchers to look back millions of years. The reason I chose this picture is because I think it's pretty. Apparently, lightning strikes more often in the LOFAR arrays than it does in the area around it. And they use this picture to illustrate that. So, LOFAR is located in Europe. And so, as you can see, there's multiple stations. Italy, France, the UK, Ireland. There is also here one in Norway. All of them are connected, and all of these antennas are used to collect data. So, how radio and astronomy works, so basically, as you hopefully most of you know, light is a radio wave. You have the visible light, that's what we can detect, but you can use antennas to detect the entire spectrum, from very small to this, like waves the size of atoms, to also very large waves. So if you go to the really low frequencies, you can have waves which are even the size of buildings. And in LOFAR, they are especially interested in these waves at lower frequencies. So these really large waves, because, well, if you go back for very long times to universe-scaled observations, then you are not really interested in the very, very high frequencies. You're more or less interested in the lower frequencies. Since in radio and astronomy, you're looking at radio waves and you're not looking at photos or pictures, you need to process a lot of data. And they have had several supercomputers at Astron located near the main site that you just saw the photo, where they do all of the data processing of all of the antenna stations. So basically at every station they do a little processing of the data, then they send it over a dedicated fiberglass network between all of the LOFAR stations to one of the iterations of the LOFAR supercomputers. So in 2004 they started with a relatively small one. Latest update, I think, in 2019 where they had a 308 teraflop computer with a 6 kilowatt usage, which is actually a pretty decent supercomputer. For all of this process they use GPUs, and one of the fun things about LOFAR is that they were one of the earlier institutes that were trying off-the-shelf GPUs instead of specialized data center GPUs. They used off-the-shelf GPUs, and one of the main reasons for them was that this was cheaper. It's simply NVIDIA charges researchers more for their GPUs than they do consumers, and they didn't need the fancy NVIDIA research GPUs, so they used the off-the-shelf GPUs. So since LOFAR is a very, very big collaboration, there is a lot of scientists involved, there's a lot of institutes involved, and it's actually quite a large, expensive research infrastructure. And by the very nature of these kinds of infrastructures, there is usually multiple experiments going on. So there is multiple research groups that are all using a LOFAR infrastructure to observe the universe. And today I'm going to talk about one of them. And that's called the LOFAR 2 meter sky survey, which is usually abbreviated to LOTS. And the goal of LOTS is to create a detailed radio image of the entire northern sky in the frequency range of 120 to 168 megahertz. So basically, they will look at the observable, their goal is to look at the observable sky for LOFAR and have like a complete scan of everything, which is a lot. As you can see, they have to, they work in observations of 8 hours straight, so they use the entire LOFAR radio telescope. They apply for blocks of 8 hours of observation time. They will focus at 3,170 points at the same time, and then they observe them for 8 hours to get a full image. Currently, they started in 2014, and these are numbers for one of the earlier publications. So that was in 2020. So after 6 years, they managed to observe about 50% of the sky. 250 scientists were involved in this project alone, and they used 14,000 hours of observation to get this amount of data. So as you can imagine, it's a really large data set. One fun fact: the reason why it's called the 2 meter sky survey is because the main frequency they look into it, which is 150 hertz, is actually 2 meters. So they have a resolution of about 2 meters when scanning. So we work together with one of the PIs of this project, Tim. And when I was talking about this with Tim, I asked him okay, why did you decide to publish? And I decided to quote him directly because he had a very nice reason. So he said, there are a lot of different scientific opportunities in each astronomical data set, so we strive to make them public to ensure that people can do as much science as possible. So the nice thing about the big infrastructures like LOFAR is basically that they publish almost raw data. So they do some processing of the data, obviously. There's a lot of noise in all of the astronomical data that they collect. They do some cleaning, and then they release data products in surveys like the LOTS, but also there's about 10 or 15 LOFAR surveys that regularly release their data to the public. Which means that anyone that has some sort of interest in astronomy and has ideas on certain observations is that they don't have to apply for expensive observation time. Rather, they can look if they can find data sets that cover the kind of research that they want to do. So this way, you don't have to find funding, you don't have to find time, and especially people can start to co-invest. So in LOFAR, you'll see that there is like many different organizations involved. All of them invest in getting as much data and as much science, as much data available for the scientists, and then the scientists can purely focus on making the science instead of having to do all of this funding. So to make this data set available, that's basically the project that we supported from DICE. We ran into a couple of challenges, and the main one would be size. Since it's kind of the entire northern hemisphere, it's a lot. It's 250 terabytes of observational data. And 250 terabytes is, by any standard, not a small amount of data. In astronomy, it's not particularly large, but they're used to work with large data sets, large distances. Everything is big in astronomy. But to make it openly available was a challenge. So usually when you try to publish your data, you go to a repository like Zenodo or an open-air repository or one of the repositories offered by institutes in your country. And usually they cap you at around 50 gigabytes. So 50 gigabytes is the maximum you can share. And then sometimes if you have the bigger repositories, or if you're willing to pay a little bit, then you might be able to go up to a couple of hundreds of gigabytes, maybe. But that's about where the default open repositories end. So we needed to have a repository that supports the open availability of 250 terabytes. And then the third one, in astronomy, they're quite used to sharing data. It's a field that has a lot of standards that should help astronomers to share their data. And they call that the virtual observatory standard. So they have a whole suite of software that they can use to find all this data that they want. So basically, you can think of it as some sort of tools to search for astronomy data. If you know what kind of data you need, you can go to the virtual observatory. You can start looking for it. So we also needed to have we needed to adhere to those standards. You had a question?
No, just a comment. That I think the virtual observatory can be thought also as a simulation of a telescope.
Mm-hmm. Yeah.
Where you, with the laptop, type some coordinates and you have the register sky and then you
Yes, that's a good addition. Thank you. So the reason that we worked together with Tim and Jan and the LOTS team is because we had part of this infrastructure available. So at the SURF we have a data repository which is specifically meant for publishing very large data sets. So we kind of had the infrastructure available to them. We needed to make a couple of changes. So for example, we were not really sure how to publish astronomy data in a correct way. So that's where we kind of had to collaborate. But at least the basis was there. So we offered a SURF data repository, which is basically a cost-effective long-term preservation solution where you can publish data sets of any size. And with any size, we really mean any size. Theoretically, if you would have a data set of a couple of petabytes, you want to publish it, and you have the funds available, we can do that for you. How? I think some of you have seen this one earlier this week. Again, we leverage our tape infrastructure. So instead of building a traditional data archive or a traditional repository, it's not completely traditional, but the most common type of repository that you will see out there will be backed by disk system. And disk, although very fast, very reliable, is not that cheap. So we use our tape infrastructure to store the data in the served data repository. And for that, so this is it, by the way. As you can see, we support communities. So there's different kinds of communities which are publishing large data sets in the served data repository. There's not that many in there because we solely focus on the large data sets. So if you have a smaller data set, then we usually tell people to go to one of the well-known data repositories. But if you have large ones, you can come to us. So currently we are we have published a couple of data sets for Astron within the astrophysics community, for the Dutch Center for Mathematics and Computer Science Research, and for a university. We completely built this product on existing software. No need to reinvent the wheel. So for the repository layer, we are using Fedora Commons, and then we have created a Drupal front end so that you actually have a nice website where you can work with all of this content. There's only one thing that we had to develop ourselves. As I said earlier, it's not really common to have a archive on or a data repository on tape infrastructure. And one of the disadvantages of tape is that tape is a offline medium. So basically we have a disk pool of a couple of hundred of terabytes in front of our tape library. Now we have a couple of petabytes of data in the tape library. And as you can imagine, only part of all this data in the tape library will be available in the disk pool at any given time. And as long as people are using the data archive, which luckily they are doing, you will see that all the time there needs to be a different subset of this entire 100 petabyte managed data online. So if you're working with a tape archive, you need to always check whether or not your files are online or offline. So if they're available on tape only, or if they are available in the disk pool. So we had to extend Fedora to make sure that we can work with that. So if you publish a data set, this is just an example of a data set that's published, you will see that the files in the data set are either online, offline, or externally available. Which means if files are externally available, that means that they are not hosted in the served data repository directly. In this case, this means that they are available externally on storage for LOFAR. Files can be online, which means they're available on the disk pool. You can download them immediately, or they can be offline. And then you see there is a small button here, a request button. So basically you can request the system to get your file online. So you will make a request to the tape system. A tape robot will go and find the tape somewhere, get the tape from the library, load it into a tape reader, find the right location on the tape, and start reading. It's basically the same as an old video band, like an old cassette, if you ever use those. So with this infrastructure being available, what we mainly had to do is make sure that we had a proper data release. So as you can see, this is actually a screenshot of the data release. It's called the LOFAR 2 meter sky survey lots. The second data release, because earlier they already did a first data release in a different, first smaller data release in a different repository. As you can see, there's a lot of authors. There is, I think, 131 listed authors to kind of show you the collaborative effort that it takes to build data sets like this. And since we have looked into using standards, if you want to check out the data set or maybe see what it looks like, this is the handle for the data set that you can use to find it. Since you don't upload 250 terabytes of data in a single zip file, the data set has been released in in multiple objects. So it consists of about 900 objects. So there will be the DOI I just showed, which is this one, is the DOI for the entire publication, so the entire 250 terabytes. And each of these, this entire publication is actually divided into 900 smaller publications of a group of observations. So basically every group of observation gets a coordinate or gets a number. And all of them together make this this release. And then for every, as you can see, the entire publication also has some metadata. This is the metadata you see here is just the general metadata that is available within the Surf Data repository. This is very general metadata. This is a kind of metadata that we show for every release. But if you would look a bit closer and look a bit further, you will see that there's some more specific metadata which is tailored to the astronomy community. Then, if you look at a single object within this entire collection, it consists of 15 files in various sizes, shapes and forms. And basically, these are different ways of looking at the same data, including some information on how to work with this data, as well as, for example, you can see here in images tar, which basically is a way of showing the process data. So it contains both the raw data and more processed versions. And again here, you'll see that every tile even has their own epic PID. So for example, if in a publication you are working with not with the entire data set, for example, but with smaller versions, or if you want to have a completely reproducible workflow where, for example, you'll have a script in which you can say, okay, download a certain data set, do some processing, etc. You can use PIDs even on a file level. So if, for example, you want to use this images tar of this specific observation, the images.tar has a PID, and you can use that in a completely reproducible workflow for others to use. So, what were some of the challenges that we had when publishing this data set? So, one of the main ones was luckily not the publishing of the data set. When I was talking to the researchers involved in this effort, they said that luckily producing the data was the hardest part. Producing the data, and that they took many years of software development to make sure that they actually got to a nice data set that they felt was ready for publishing. But that's also why they like to publish it, because of now by publishing this, all of this effort can actually be prevented for others to do. Another challenge that they are actually still facing is to arrange a long-term infrastructure and support. So one of the nice things that DICE did for this community is that DICE helped with the publishing, so with all of the effort, the human effort that was required in doing this work. But DICE also paid for the infrastructure during the duration of this project. So it's not cheap to run to store lots of data. And unfortunately, as with anything, everything in life, somebody has to pay for it. And in this case, it was DICE. But since DICE is ending, Astron has to look for a new source of funding. Unfortunately, we can't do it for them. We have heavily subsidized infrastructure, but the infrastructure is still not free. And this is something that you see quite often when you're looking into open publication of data, preservation of your data. It's really important to start looking early for sources of funding because it can be a bit difficult, even though we would like to see this differently. Then the other two challenges both have to do with the size of the data. So the single files, even though the entire publication is split into various tiles, each tile still has quite large files. So you already saw just now that the images.tar is about 1.8 gigabytes. But a lot of the files with observation data, with raw data, are about 600 megabytes in size, which is large. If you have to download a 600 megabyte file using a browser, it's possible, but it will take a while. So for a researcher to work with this kind of data can be a bit difficult. Especially what we're also seeing is that the virtual observatory tooling that exists at this point is not completely capable of handling files of this size. So if you're going to use this data set in your virtual observatory, you might run into problems. The nice thing about the astronomy community is that they like problems, they like challenges. So they're actually using this data set to test and make this virtual observatory tooling work with larger files. And also work in different ways with data sets, for example. So Tim told me that they're currently working on a way to, for example, have slices of data available. So, since I see the bus arriving, and I'm actually also arriving at the end of my slides, I'll start wrapping up. One of the main things I wanted to know when I was talking to Tim is what did they actually gain from publishing? Because it took quite some effort to make the data. It took quite some effort to make the data available. A couple of us spent a good couple of months on doing this, including Tim and his team. And he told me that to date, our publications describing our LOTS data release have received over 900 citations, and we believe that the data has been directly used in over 300 publications. And I think that sentence kind of shows why you want to do this. So I think earlier this week we already talked about making your data fair, making your data available, and that some people say that if you publish a data set, it won't improve your H-index, it won't get you any citations. Well, I think this is kind of the proof that it actually can. So even the publication in which they describe their data, so it's an interesting publication, but it's not groundbreaking scientific work. Got 900 citations, and even they contributed to the creation of 300 publications. So, like Tim said, these numbers imply that they are reaching a large number of researchers and looking more at the publications. We see that the data are used for a vast array of studies, right from exoplanets through to the cosmology and at scales between. So basically, this data set enables a lot of astronomy research, making all of this effort, I think, completely worth it. So with that, I would like to thank you for your attention. If you've got any questions, I think we have time for them because the bus is, it's leaving in 20 minutes, so not too many. Yes.
So since the beginning I have this question actually. Why did it not splitting this large data set into smaller ones since the beginning?
I think I'm not completely sure because I'm not super much involved in the science in this one. I think it has to do with the way they perform their observations, and they want to keep everything that is in a single observation together because that's basically the structure of their raw data. So you can go splitting further, but then you would for some use cases and probably their own use cases, it will be harder to work with the data. Because you would have to combine multiple publications to look at one observation.